shear behavior of section. So far we have been talking about bending moment and exit forces, and today we will start the topic on shear and torsion. So basically we will now concentrate on these actions: shear about vertical axis, shear about horizontal axis, and torsion about the longitudinal axis. So there are two shears to be taken care of together with the torsion. Normally when you do beam design, you only deal with one shear, which is the shear perpendicular to the direction of the loading. But because last time we said that we will not distinguish between beams and columns, so we know every cross section. So shear can actually come in any direction, just like moment. But we can have two components, one along this way, one along that way. One we normally call major shear, and the one we will call minor shear. So we will be dealing with both the shear design, because in columns both shear are possible and present. In fact, mostly the shear is inclined and we have two components. And then comes torsion together with that. And torsion tries to twist the cross section. And again, it is almost always present in every member. And engineers have been, torsion is an interesting design issue. We will talk more about that, because it's just like one of those things that people have been quite ignorant about torsion, and unfortunately now we cannot ignore it, because torsion has become a serious issue when combined with shear, and we will talk more about that. Unlike flexure or bending, where we developed a single equation for all kinds of members, there is no such unified theory yet. There is one. Sorry, we started a bit early. So there is no single equation that I can give you that will solve all of the shear and torsion problems, unlike the one that we have developed for bending and axial load. And there are many reasons why it cannot be done, and we will understand that as we go along. But there is a way to deal with them in a single unified manner, which we will discuss in a separate topic, not in this topic. So no unified theory yet, several interactions, and because the reason is shear, torsion, shear, moment, shear, load, and torsion and moment. So many interactions going on there. So that is this is an interesting interaction between shear and load. Bending moment can be any place, doesn't matter. But for shear, the location of the load is also an issue with respect to the supports. So we will also have to consider that. So it's not just the value of the shear, but how far is the load located which is causing the shear. Or sometimes we call it shear span. So those will be also important. So we will talk about something. Because of all of these interactions, unified theory is not really practical yet. People are working on it. Many are there, but none of them really solves all the problems. Then effects of confinement, flexion reinforcement, and hoops has to be considered, because we put transverse reinforcement for confinement, but it also becomes a reinforcement for shear and also for torsion. So one reinforcement serves many purposes. So we don't know which part is confinement, which part is for torsion, which part is for shear, because we have them all coming at the same time. So one reinforcement serving 3 or 4 purposes. So how do we know which part of the reinforcement is doing what? Or how to combine those reinforcements together so they serve all the parts? For example, if you have a column and you put the stirrups around that as a confinement rebars, and we utilize all of their capacity for confinement, and now if shear comes, where will it go? Or if you put the stirrups and you did not intend to use it for confinement, but because it is there, it will automatically start acting in confinement, because you can't stop it. When you apply the axial load, whether you design for confinement or not, stirrup is there. So it will automatically confine the concrete. But at the same time, there is also shear. So then what happens now? Which one takes priority? So these are many issues in this interaction that make this problem quite complicated. Current approaches, solid mechanics approach, principal stress, Mohr circle, we will start with that. The first approach is assuming that the concrete is a solid, is a single material, and we can use solid mechanics theories over there. Second is truss mechanisms, strut and tie diagonal tension models. We will talk a lot about these, especially later we will have a separate topic on this truss mechanism, strut and tie approach, right? Compression field theory, this is the theory that most often people use for beam design. Compression field theory. They follow the compression. Arch action, double action, fracture mechanics, aggregate interlock, and other considerations. So there are many things to be considered in this shear problem, unlike bending, which is much simpler in many ways, right? Okay, so now we know that we are dealing with a difficult problem. So let's go into it one by one, because you need to see these colors. Basically, this is solid mechanics. We are assuming that the concrete beam is a single material. It has no aggregates, no cement, just a material. And it has uniform properties everywhere. And it has no tension problem, no compression problem. It's just a material. If we have just a material, then we get, and if you apply the shear in this direction, apply the force, and the shear is acting like this one. What is shear basically? It's trying to separate two parts of the section perpendicular to that section. But that is pure shear. That you take a thing and then you try to cut it on a plane directly up and down. So there's a section here, one is staying here, one is going down, it's called shear. That is called pure shear. That means no other thing happening, just pure shear. When we use a scissor to cut something, we actually do it in shear. We shear it. We have two parts of the scissor. One keeps the body in one place, second part cuts it straight, and it's shear. When we shave, not you, but guys who shave, the shear. We are basically doing shear, right? So shear is what we do when we cut something exactly at a section at a plane without causing any other stresses. Pure shear, if you apply and try to cut the section like this, it will develop stresses in this manner. Stress will be 0 here, and its stress will be maximum in the middle, and then go back to 0 here. So that means the section resistance to shear will come from the middle of the section, not at the top, not at the bottom. So most of the resistance to shear will come from the center of the section, and it is not uniform, right? So this is first important thing to recognize, that the shear stresses and shear resistance depends on the location of the section. Just like when you bend something, what happens? The maximum resistance comes from the outside corners, right? Maximum tension and compression at the edges, nothing in the middle. This is opposite to that. Shear is completely opposite to bending. Bending, all the stresses are at the edges, nothing in the middle, 0. Shear, 0 at the edges, maximum in the middle, right? And you might think this is a good thing, but not. We will see later. So, and this is torsion. Actually, unfortunately, you cannot see the colors clearly. Maybe if I do it like this, you can see some idea how the colors look like, right? So basically, there is a variation of the stresses. Now this is where the things get a little bit interesting. Torsion produces shear also on the plane, right? It is just that unlike shear, which has a variation like this, starts from 0, comes like this, goes back down, and it is constant from here to here on the section, but varies like this, Torsion is not like that. Torsion is high at the edges, here, 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 and then 0 in the middle. And when you twist something, the edges of the section, they all become in torsion and shear. But the shear is going to be up and down. So one shear is going to be like this, one shear is going to be like this, because torsion is doing like this. So torsion is a couple, is a moment on the section. One part of the section will try to resist this way, another one this way. So an internal couple will be made in the section from the stresses, shear stresses, which will be acting counter to the torsion. So torsion is going like this, the couple inside is going like that, right? So that will create maximum stresses at these ones and nothing in the middle. So torsion, shear stresses due to torsion exist maximum at the edges and nothing in the middle. That's why box sections are the best for torsion, because they provide the material, or the tube, hollow tube is the ideal size section for torsion. That's why all of the twisting shafts and mechanical things, they're circular. So a pipe is the best to resist torsion because it has the material right at the location where the torsion is required, and all of that is constant. Because the thing is, when we will go into more detail, but imagine if there's a torsion here, right? It's twisting like this, so internal stresses are developing, and they are acting on the center. So from center to edge, they're forming a couple. And if the distance of all the stresses is equal from the center, it is perfect. Uniform stress will be generated. If the distance is different, more stress here, less stress here, because the distance lever arm is shorter, so the stress must be higher to equal the moment, because moment is constant. Correct? So that means the stresses on the section will vary based on their distance from the center to the edge. The farther the edge, smaller the stress. In this case, if it is circle, constant in that case. And in the middle, we don't have any stresses because we want the stresses, we want the maximum resistance to torsion, which must come from the as far from the section as possible. Right? So we will go into more detail, don't worry. Right now, just the introduction. So shear stresses vary like that, 0 at one edge, and if we have shear coming this way, this will form a stress like that. Right? If you have diagonal shear, then a complex stress pattern will exist on the section. Right? Now combine it with torsion, you will get a combination. In one location, this shear stress, which is positive, will add to the positive and will become very large. On the other side, torsion stress is negative. This is still positive. It will become 0 or negative or small. So when you combine torsion and shear together, in one side of the section, the stresses will go very high, and on the other side, they will go very low, because torsion is producing negative and positive stresses on the section, whereas shear is always producing positive stresses. So on one side, positive and positive will add, on the other side, positive and negative will subtract, and depending upon which is more, torsion or shear, it may become negative or very small positive. Right? So this is the kind of complication that we are dealing with in shear torsion interaction, and we haven't. And torsion has another problem. Torsion has a direct interaction with moment, because torsion produces another property I told you last time.
Warping.
Warping. And warping is axial also, because warping has raised to power 6. 4 parts coming from torsion, 2 parts coming from bending. So that means torsion is connected to bending, and torsion is connected to shear. So shear is connected to bending indirectly. Correct? Through torsion. So now we have this whole interaction happening. That's why we need to separate this problem and try to solve it one by one. Everyone clear about that?
So is that a maximum at the middle and torsion?
No, that's the colors are not showing, but you see basically this is 0, maximum here, because the color blue is supposed to be high value. This is actually, the colors are not right. This is another color coming out to be blue. This is purple, actually 0. That's why I reversed it here so you could see that. Anyway, in your lecture, when you go back, you will get the real colors on your computer, so don't worry about it. Some more plots on complicated section. Some more plots on complicated section. These are all drawn by our program that we developed here called Section Builder, which I will give you a free copy, which you can study all of these things by yourself. All right. You can try section, you can study all of the shear stresses, torsion stresses. You know, it's very interesting just to be able to generate these stresses for different sections. Okay. any section that you create, the program can generate the stress profile for that. For assuming it's a solid section, okay? So you can see from here T section, the stresses will go like that. T section, otherwise that means if the shear is like this, profile will be like this. If shear is going the other way, profile will be like this. If shear is going this way, profile will be like this, right? Box. Similarly, if you cut the section, in that program you can cut the sections and see the profile also. Section builder. Okay. This I will remind me to put that on the server so people can. It's supposed to be a licensed program, but for the class I removed the license so you can use it, right? And then interesting is when you put a steel section to material, what happens then? Obviously, modular ratio comes in, and the material with higher modular ratio will take more stresses, and then all the stress will go into steel section. Nothing in concrete. 10 times more here than that one. This gives us a very good idea that if you have a problem in concrete in shear, right, put the steel section inside and the shear problem goes away. Right? And this is exactly what we do in flat slabs or slabs where the shear, punching shear is very high. We put steel sections crossing grillage in the plan, and all of the shear problem goes away because steel takes all the shear, and steel is very good in shear, especially the web, right? Flanges take nothing because flanges are far, that is zero rotation. So all of the shear, in fact in a steel beam, all of the bending is taken by flanges, all of the shear is taken by web. It's a perfect, I section is the most, I would say, actually box section, but okay. Box section is the most efficient section of all sections. Steel box section is perfect section in every way. It can take torsion, it can take shear, very nice in both directions. It can take bending in both directions. It is a perfect section. A box steel section is the best possible section that you can get for bending, shear and torsion, right? This is an example of that. So shear will be like this, torsion will be, you can plot. Unfortunately, you cannot see the colors here, but in your notes you will see them, all right? So you can see how the variation, and this is also a very good section, concrete box section. Because in box section, we take away everything which is not needed and only leave what is more useful, right? So that's why, we can optimize section by looking at the stress patterns and so on. So what we learned so far is, number one, shear produces stresses, shear force produces shear stresses which vary along the depth, maximum in the middle, zero at the corners. Torsion also produces shear stresses which are maximum at the outer edges, nothing in the middle, right? But they're opposite, there's a couple, direction changes based on the torsion direction. And when you combine them together, you have very large variation in shear stresses on the section. And also, we have this kind of variation because there's more area here, so the stress drops, right? Normally, if you don't have this one, this will continue like this. But this is dropping because there's a more area here to take care of that force. So the stress drops. But the total force is actually more here. Stress multiplied by this web area, correct? But it's not so efficient. So that's why here, and then you increase this one here because there's a more area, suddenly small area, stress increases at that point because the force must be maintained, right? Clear? Some more sections. Twisting torsion, you can see the colors and you will find that they form, this is interesting. The torsion flow goes like that. The torsion flow goes like that. The torsion flow goes like that. It follows the section. It goes like that. It goes like that. In all of these cases. So torsion stresses just flow around the edges, around the corners, around the boundaries, right? And that torsion flow, this idea of torsion flow has actually simplified torsion design a lot. Until people realized that there's a torsion flow, the torsion design was a very complicated problem before 1977 or something like that. After 1977 or I cannot remember exactly, 83 code, they changed the torsion design procedure, made it very simple. Before it was really, really complicated. right? Knot has become simple because of 2 or 3 theories that have come up. Alright, so you can see the torsion produces all this, and this section is beautiful because this flow is constant and it's very efficient for torsion. Right? This is also good, but values will be smaller here, higher here. Right? So not so efficient, because if the thickness is constant, then you are not using the material most efficiently. And this one is fine. You can really make it very thin and then make it very good. But bending capacity is not good for circular sections. Right? So this is good in bending, this is good in shear, this is not so good in shear, very good in torsion. So we have to choose the sections based on what they are good for. Again, combination, this is this one plus that one. This is the shear with the sign, so that when you do this one, you will find variation. So shear plus torsion can produce very, very complex stress states in a section. Please remember, we are talking about a solid section. We are not talking about cracking yet. We are not talking about concrete being weak in tension. We are not talking about concrete being weak in shear yet. This stress state will never exist in reality, because concrete will crack in some locations and the whole thing will be changed. And that is why we cannot use these theories completely for the shear design. We have to come up with something more different than that one. Right? If it was just another material, steel will be fine. We could combine them, but we can't. Shear and torsion cannot be combined anymore, because one direction it's already cracked, so the stress doesn't appear. It's a cracking already. Stresses are gone, right? Because of the cracking. So you can't add them. Things that are all shifted. Cross section is no longer the same. So because of those complications, we cannot use these things in real design. But they give us an idea where we are coming from, right? So shear stress distribution contributes to, now let's go back to our strength of material force, principal stresses. Everybody knows what's a principal stress. What is a principal stress, by the way? Let me not assume that everybody knows. What is a principal? What are principal stresses?
Axial and shear stress are principles.
Something like that, right? You have some idea. What are principal stresses? Principal stresses are the resultants of the stresses in such a way that we have two primary directions, the maximum stress direction and a minimum stress direction, right? So you get the principal stresses by calculating the component from all the stresses, and the one which is pointing to the maximum plus, it becomes the one principal direction. One which is pointing to the plus minus, minimum one, becomes the, or minus becomes the other principal stress. So maximum and minimum stress directions and stress values in a section become principal stresses, and they are always perpendicular to each other, right? And on the one of the properties of the principal stresses is there is no shear stress when we are talking about principal stresses, because these are already resultants in such a way that only the axial stresses exist on principal directions or principal planes. Shear stresses disappear. They are converted back into the axial stresses because they are still, they're just stress direction that they are added. So that is the Mohr circle. How many people remember Mohr circle? You remember something. A circle with this one, this one. That is a relationship between axial stresses and shear stresses. And that, depending, because circle, why is it a circle? Because that's a failure criteria. Combined shear and axial stresses have a limit, which is a principal stress, right? Out of that, some part can be shear, some part can be axial. If axial is more, shear will be less. Less will be left for shear. And when you reach maximum axial, zero shear automatically. Correct? Same is the case if you have all of that, then that is shear, nothing is left for bending. So it's a transformation between shear and bending stresses. And some must always remain the same, which is the principal value, maximum value of the material, right? So that's why there is a circle of the stress. And on that you can have any angle. So the stress directions, component, the stress resultant direction will determine how much shear, how much axial, right? So we come to that in another minute. So one of the principal stresses will be tension, that is another property, maximum or minimum. Concrete does not take tension, now we get into trouble. Because we are talking about a solid section which has principal stresses, because we have tension and compression, or axial stresses and shear stresses. There are only two stresses in the world, or okay, not in the world, in our system. Axial and shear. That's it. Do you have any other stress that you can think of? Exam stress is different. On the section, only you have axial and shear. And we will soon find that actually shear stress is no such, if you go to principal direction, you only have principal stress. That's it. And components can be shear or axial, right? So, but one of the things is that one of the principal stress is tension. And we normally say that concrete does not take tension, which means that now what will happen if one of the principal stress cannot be taken? What happens then? How do we solve the problem if that stress cannot exist? We calculate a stress which does not exist. So what do we do? Sorry?
Say 6. Something else.
Yeah, let's see what is something else, right? Because we calculate a stress which does not exist. It cannot exist. So how do we calculate it? It doesn't exist. It cannot exist. So we have to find out a way to incorporate that into our model. So concrete does not take much tension, so concrete cannot resist much shear stresses, because shear will produce tension. One of the stress from shear will be tension, one will be compression. So theoretically speaking, if concrete cannot take any tension, according to Socrates' theorems, concrete cannot take any shear. End of story. So where we studying about shear, concrete cannot take any shear because it cannot take any tension. And one of these stress from shear will always be tension. So there you are. So problem solved. Let's go home. Concrete takes no shear. Finish. And that's exactly what BS code says. BS code says don't waste your time and energy on all of these things. Concrete takes no tension, concrete takes no shear, all shear must be taken by reinforcement, simple as that, right? But ACI still says no. Concrete does take some tension, let's try to make use of that, right? And that is where all of your complications come from, that we are going to talk about. And it's very interesting, funny in fact, when we developed the bending theory, what did we say? Concrete takes no tension. So we are saying in bending, ACI is saying, bending, concrete cannot take tension, but shear, it can take tension, which is not really correct. One of them is not correct. And in fact, now gradually ACI is moving to the same conclusion that concrete takes no tension in shear. Forget about shear capacity of concrete. In fact, for earthquake design, we do not consider the shear capacity of concrete anymore. That is the bottom line. So if we can say tension capacity of concrete is 0, shear capacity of concrete is 0, our life is much simpler. Very easy, right? Okay, but unfortunately not yet. Let's make it difficult a little bit more. This is another beam in which we have bending and we have shear. Okay, so these are those acting here. So any section A and B, if you cut this one very close together, you will have a bending moment here, you will have a shear here, right? One side like this way, so that's cutting down and also it's bending. And so on the section you have this thing occurring, shear and moment, shear and moment. At any given section, they are always there, except in this particular case, moment will be 0 here, and shear will be 0 somewhere along the beam. Correct? So there are some sections where you have 0 moment and some section where you have 0 shear. But most of the sections you will have shear and moment acting together. And that is the problem, because moment will cause axial stresses, shear will cause shear stresses, and they will exist both at the same section. Right? So they must interact. Clear? And this is the one that we are talking about, shear and moment interaction, that we have to consider. Now, let's take one of those points on that section, on the beam that I showed you. One element on that section, and you will see that this is a shear. So shear must always be like this, on one element on the side of the beam, not on the section, but side of the beam, on very small slice that we talked about. This width is very small, nearly 0 at the section. So the stresses exist like this, and shear stresses, this one and this one on the two sides you just saw, right? They must balance, and this must balance that one because they must be in equilibrium. Correct? So that means shear stresses, vertical and horizontal shear, exist simultaneously at every section. So vertical shear also produces horizontal shear because that is the nature of the shear. Otherwise, this will not be in equilibrium. Correct? So you can imagine that these two force stresses and these two stresses are actually going like this. They are going to make this rectangle into this trapezoidal shape. This two will push this way, those two will pull that way. So the element will become like this. When the element becomes like this, it will try to break at this location. Tension will come in this direction and compression will come in this direction. So you can imagine if it is being pulled like this one, compression force is acting like this, tension is acting like this. Clear? These two are, the vector of these two will be like this, pulling it this way, causing a tension here. And on the other side, here, two component, pushing it inwards, causing a compression. So on this section, we have a compression stress and we have tension stress existing, right? And this becomes our principal plane where there is no shear, only now tension and compression or axial stress is left. Correct? From the Mohr circle, there will be a plane where shear will disappear, and we will get this is that sheet plane on which only tension and compression exist. No more shear. Shear has been converted into tension and compression, and that's what we were talking about. That one of them must be tension, one of them must be shear. Now it will break here. If we say concrete has no tension capacity, 0. If sigma T is equal to 0, it must break here and it will become failure and this section is gone. It cannot take any force at all. 0 shear capacity. Correct? But if we say that concrete has some tension capacity, then the stress that can exist here will be equal to the tension capacity of concrete. So that means it can take just enough shear until concrete cracks in shear. Correct? And last time I told you that every time you see FC and under it is a tension capacity of the concrete. So that means we are saying that concrete can take a force equal to 2 times, stress equal to 2 times under root FC prime. This is the equation from ACI in MK unit, and in foot-pressed unit, in other units this number F2 could be something else, right? Doesn't matter. But it takes some fraction of the tension capacity to be equal to the shear capacity. Correct? And that is the basis for our shear design, that based on the tension capacity we calculate how much shear can be taken, and that becomes the shear capacity of section. In fact, it is the tension capacity of section. There is no such thing as shear anymore. We are just dealing with tension. which is negligible, but okay. And if the stress exceeds this one, we could put a bar perpendicular in the tension direction. So all of the tension could be taken by the steel bar, and all of the compression could be taken by concrete. Then we have no problem. Then we can put some shear on it. So now the shear capacity will depend on the shear capacity of the steel, right? Putting directly perpendicular to the crack. Those of you who, okay, very long time ago, people used to do that. When I started practice, we used to do that. We would provide the shear as diagonal bars in the shear zone like this. We thought that that was the way to do, because there's a crack, so we put the bars, so we will put a diagonal bar, series of diagonal bars in the ends of the beam, bent up bars. So bending bars will come in, and close to that we will just bend them up, and then they will become shear reinforcement. It was very efficient, very good. But then people in the West, they said, no, labor is too expensive. It takes too much time to bend those bars, and it's too complicated. You know, it's not worth it. Labor is more expensive than material, as you know over there. In Asia, design is based on material economy, and the West, design is based on labor economy, right? So they said labor is more expensive than material. Let the material be wasted. We will put the bars like this, even though their component is only we can use, because if you put the bar like this, we can only use one component of that along this one. Another component will be not used. But we are okay with that. We don't mind that because it's easy, simple. And now we don't use diagonal bars anymore. We use stirrups like this and stirrup spacing. So number of stirrups crossing this crack is calculated based on the total force you need, and then take a component of that, and then you're done. Right? That's all we are doing. Shear design is only that. We calculate what is the total stress in this one here, tension, multiplied by this length, which will be the total force. Then you calculate the required reinforcement, take the component, and then you design. In fact, this length, you take that one, it is already the component. So instead of taking this diagonal length, you take the vertical length, and then you don't need to take the component. So based on a simple arithmetic, we can calculate how much steel is needed to take all the tension from shear. So the procedure, normal procedure is that you first of all, you calculate how much capacity can be taken by concrete, you subtract that, remaining amount, you calculate the steel and provide that. British say, no, forget about that, all of the tension taken by steel. But if the shear is very small, it is less than the tension capacity, okay, no reinforcement required. But if it is more, forget about the concrete. So this is all about shear design. I wish it's not. Why? Why can't we just end it here? What's the problem now? The problem is, as I mentioned to you, on the section we do not have only shear stress. We also have bending stresses, which are interfering with the shear stresses, because the principal stress depends on the combination of shear and axial stresses. So if there is an axial stress, that will interfere with this whole system and make it fail. Suppose there is a lot of tension, then that tension already exists. Shear tension, tension must be combined. Compression tension must be combined. So now we have another. So let's go to the next step and see how that will work. This is how it will work. This is the beam now, subjected to bending moment and shear. In this location, if that section is located, you have zero shear. Let's say center of the beam, UDL. No shear, maximum tension, maximum compression. Correct? In this location, some bending, some shear, some compression plus shear, some tension plus shear. In this location, only shear, no moment, right? So you can imagine that this variation will change along the entire beam. So no single value of the shear principal direction can be calculated based purely on shear, because the axial bending moment is also changing the tension that you are trying to provide for shear, correct? because that is derived from principal stress concept, war circle. So the angle of the shear, amount of the tension and angle will change. In the middle, the tension is like this, right? Completely horizontal because there's no shear. This location, it's a 45-degree angle because there's no bending moment. In between, it will be like this. So it has to go from horizontal to 45-degree and exactly above vertical. Correct? Because stress must be vertical then, close to the reaction. So from completely horizontal stress position, we will gradually go to a completely vertical position of the support. Shear will be maximum when we have 45-degree angle. That means that equation that we develop under root Fc prime, simple one, cannot be applicable everywhere because the tension is not constant. That equation was developed for pure shear, not developed for any other equation. And on top of that, add torsion now. So the two faces of the beam, because of torsion not having the same stress, and in between stress is changing also. So we are not having constant stress, shear stress in the beam. Two faces because of torsion, one face in tension, one way in compression, pure torsion, right? So we have another problem there. So you combine torsion and shear and bending together, we have a problem. Then let's say it's a column. You also have axial force coming from the outside. So add that axial force to this one, subtract from this one. So we have another issue coming. Then we have a shear going this way. This is only one directional shear. We have two directional shear. So we have two directions of shear interacting with each other. We have torsion also coming in. We have axial force also coming in. We have two bending moments coming in and warping coming in, changing all of the stresses and strains in the whole section. The core section is really in trouble, right? You can see from here, pure shear, tension plus shear, compression plus shear, torsion plus shear, torsion minus shear. Independently, we haven't talked about this plus that and that plus that, and there are so many possibilities, correct? But all I want to know, I want you to recognize is that this is not a simple problem. This is a very complicated, complex problem that we are facing. So there is no, that is why there is no single theory. That is why there is no single solution. That is why we have to go to the approximation that we will go in very soon, right? Any questions? Do you understand the whole stress state in a member right now? And variation along the length. And this is a simple beam. What if we have a negative moment and then positive moment and some point loads coming here? Then this is not pure shear. This is also a lot of negative moment, which also has tension and compression. So the support is no longer pure shear. Pure shear disappears, right? So bending moment diagram, bending moment variation will also affect this concept. And because of all of this, last edition of ACI, they have 6 or 7 equations to calculate the concrete capacity in shear. Because of all of these situations, they try to take care of each one of them, right? And they say, okay, if you're too lazy, you can assume this case for the entire beam. But if you're not too lazy, you use separate equations for each case, right? Based on how much moment, how much axial force, how much torsion is present. Okay? So there are equations from very simple to very complicated, right? Okay, anyway, this, as you can see here, is the way the stress patterns will come, and the crack will be perpendicular to that. This is the trajectory of the principal stresses, right? And the cracks will be perpendicular to that. So the crack will run like this, crack will run like that, and this is the complete. And this is all based on principal direction problem and concrete shear capacity. But there are many other complications. Concrete is not a simple material. There are stones in it. There are aggregates. So when a crack develops and a crack is coming and there's a stone there, it cannot go through the stone. Sometimes it has to go around the stone, right? Because the stone is stronger than the paste. Depends what kind of aggregate you are using. Sometimes the stone is weaker than the paste, sometimes the stone is stronger than the paste. So depending upon that, the crack will change its direction because there are two different materials there, right? And that's why it becomes more complicated, and then the shear problem is not simply shear, it's also aggregate interlock, because aggregate interlock is causing shear friction and other things are coming in, right? So shear has pure shear, which what we are talking about, plus it has aggregate interlock, plus it has shear friction. What is shear friction? Shear friction. Can I borrow one cell phone and the other cell phone? Okay, I can use mine. Okay, give me one. Thank you so much, it's nice. Okay, if I put them together, right, I can move them, slide them a little bit like this. Right? However, if I press them, I can't slide them now. This is shear friction. Axial force and friction have a relationship. So that means the shear is not produced because of the friction between two materials, which is related to the axial force. So another shear comes in, shear friction, right? So shear friction, normal shear due to tension, principal stresses, and interlocking shear. So three shear components will be then activated, making it further complicated. Right now we are ignoring aggregate interlock and we are ignoring shear friction. We are only talking about pure shear coming from principal direction stresses, right? So it is not going to match with the real world, because real world also has shear friction and aggregate interlock, which we might discuss separately. These are some of the samples, cracking, pattern you can see from here, tension developing, shear failure, pure shear failure, falling down, and then this is all coming because of those principal directions and tension and having no reinforcement. Other problems that we will talk about later, just to give you an idea that we are not done yet. B and D regions. You heard about these? Have you heard about the guy called Bernoulli? Bernoulli? Bernoulli's theorem, Bernoulli's equation, Bernoulli's theory. Okay. There is, Bernoulli. Bernoulli's theory of concrete or section assumes plane sections remain plane, right? Which we already know that it is not true, but it's true actually in some portions, not true in some portions. So the regions of a member or a member, parts of the member in which Bernoulli's theory holds nearly true, is called B region, and the portion of the beam or members in which Bernoulli's theorem or theory or assumption does not hold true are called disturbed regions, D regions. That means they are too disturbed, stress strain is too complex, we don't know what's going on, so we call them disturbed, D regions, right? So we can divide members into B regions and D regions, and then you will find later that whatever we have studied so far about the bending theory and whatever we have studied for shear only applies to B regions, does not apply to D regions, right? We have a separate lecture on D regions that we will talk about. So let's just to make sure that you understand that this is not, we are not solving the entire beam yet. We're solving part of the beam, part of the column, part of the problem in which Bernoulli's theorem nearly holds true, correct? In which plane sections are assumed to remain plane. Okay, so we'll come back to this in another lecture. Then comes the concept of the average stress, because the stress is changing all the time along the beam. We have seen from the moment is changing, shear is changing, stress is changing, right? But the cracks, when they develop, they redistribute the stresses. So when a crack develops, there is like a weakness. So the stress is in between because these are weak points. So between the cracks, the stress becomes nearly uniform, equal to the capacity of the stress at the crack. It's obvious, right? If the stress is high, it will develop a crack, and then again the stress next time it's high, it will develop another crack. In between the crack, the stress is normally almost constant, equal to the capacity of the concrete in that location. So we get this idea of small portions of average stress, which we can use between the cracked locations for our design purposes. Assuming that the stress is uniform in that portion, we can use the average value and use that in the calculation rather than calculating it for every location or every variation. And this is the, you can see between the two cracks, this portion, one stress zone, second stress zone, third stress zone, like that. So we can have average stress concept here, and based on that we can assume the stress, instead of that what we assumed last time, going like that, it becomes more or less like that, because in the below portion the reinforcement comes in and that takes care of the stress. The stress is high, so this distribution of the stress, shear stress, now changes. It's no longer like we had last time. Because of the cracking and because of the reinforcement starts to take extra shear, which is at the bottom. This also takes some tension. Because of that, we get this. So we can see that the uniform average stress becomes in this manner rather than the original one, because of the cracking, because of the presence of reinforcement, which we ignored in our original plots, right? So this is nothing complicated, just to give you an idea that the equations and theories are developed on the concept of the average stress, and they take into account these crack spacing. This spacing is typically equal to, related to the D, approximately. This one, nearly. This is like a square, right? But sometimes these cracks can be closer together if the reinforcement is not provided properly, right? But for the purpose of design, we assume this to be the case, right? And then we can distribute the reinforcement in between. We will go gradually to this point, like this. So average stress, shear stress between cracks is then calculated based on the moment change between two locations, and you can study these equations, and then finally it comes out to be in that manner. Please study this equation, understand it. If not, then we can discuss about this. This is part of the assignment that I gave you, calculating the concrete capacity and how the average stress works. This is, when you read the SCI code, you will find that this is the basis for deriving those equations. So we have a compression here, we have a lever arm, we have a tension here, they form a couple, and based on that they can shear, they can resist moment and shear together, and after that simplification we can come up with that equation. So what is interesting to see is T, the reinforcement that we provide also contributes to the shear design or shear strength, because it provides us, like I mentioned, it provides us the tension. So whether we provide the reinforcement vertically or horizontally, it will have a component diagonally, right? Always. So that means shear reinforcement can be horizontal or can be vertical. It has some effect, some contribution, and that is what we will study when we talk about walls, right? And beams. So we will see that the shear reinforcement actually could be provided in both directions. The effectiveness will be less in horizontal direction than vertical direction because of the interaction of the other stresses that are present there. Because why? Why? If you provide horizontal reinforcement, that reinforcement will be mostly taking the tension coming from bending. So its shear effectiveness is less. But if you provide a vertical reinforcement, bending has nothing to do with it. So all of that is available for shear. So that's why it's more efficient to provide along the shear than perpendicular to the shear. If there was pure shear, no bending, either direction will be fine. Right? So this gives you some idea on how the equations are derived and how the total capacity is calculated from this lever arm and capacity of the reinforcement. Okay. Spacing. This spacing is typically equal to, related to the D, approximately. This one, nearly. This is like a square, right? But sometimes these cracks can be closer together if the reinforcement is not provided properly, right? But for the purpose of design, we assume this to be the case, right? And then we can distribute the reinforcement in between. We will go gradually to this point, like this. So average stress, shear stress between cracks is then calculated based on the moment change between two locations, and you can study these equations, and then finally it comes out to be in that manner. Please study this equation, understand it. If not, then we can discuss about this. This is part of the assignment that I gave you, calculating the concrete capacity and how the average stress works. When you read the ACI code, you will find that this is the basis for deriving those equations. So we have a compression here, we have a lever arm, we have a tension here, they form a couple, and based on that they can shear, they can resist moment and shear together, and after that simplification we can come up with that equation. So what is interesting to see is D, the reinforcement that we provide also contributes to the shear design or shear strength, because it provides us, like I mentioned, it provides us the tension. So whether we provide the reinforcement vertically or horizontally, it will have a component diagonally, right? Always. So that means shear reinforcement can be horizontal or can be vertical. It has some effect, some contribution. And that is what we will study when we talk about walls, right? And beams. So we will see that the shear reinforcement actually could be provided in both directions. The effectiveness will be less in horizontal direction than vertical direction because of the interaction of the other stresses that are present there. Because why? Why? If you provide horizontal reinforcement, that reinforcement will be mostly taking the tension coming from bending. So its shear effectiveness is less. But if you provide a vertical reinforcement, bending has nothing to do with it. So all of that is available for shear. So that's why it's more efficient to provide along the shear, that perpendicular to the shear. If there was pure shear, no bending, either direction will be fine. Right? So this gives you some idea on how the equations are derived and how the total capacity is calculated from this lever arm and capacity of the reinforcement. Now, what is this?
Truss.
Yes, of course. This is a truss, real truss, made in steel. So what do we see here? What are these colors indicating? Two colors.
Compression and tension.
Compression and tension, right? So very clear. We know when you apply the load, we have tension here. These are in tension, these are in compression. We are very clear about that, no confusion, right? Absolutely. Okay. What about beam? Concrete beam. You have stirrups, you have longitudinal bars, right? Same blue here. So there must be a hidden yellow inside that is working, and that is true. We know there is a compression at the top. Just now we found that there is a compression along the shear direction. So there is a compression here, which means that there is no real difference. In fact, there is no difference between a truss and a beam in terms of the mechanism. It is just a hidden truss in a beam, right? And we will see later that this will lead us to a very nice, good theory to combine shear and bending moment together into one model that we will be talking about, the third part of the study. Integrate axial force and bending moment, integrate shear and torsion, and then go and combine them all together. So this is the link between combining them all together, because we can see that the truss and and the beam are the same, and bending and shear are actually all combined into this thing. Axial force, truss is stable because of axial force, only axial force, right? No shear, no bending moment, correct? Yes or no? That means we only need axial force, or we only need axial stress. There is no such thing as shear. There is no such thing as shear right here. Truss is fully stable and carrying all the load purely by compression and tension. No need for shear, correct? Shear is converted into a diagonal force. Same thing in concrete. So we can completely get rid of the shear thing and only deal with axial compression and tension, which we know how to deal very well. Correct? So we will jump from here to here and then forget about the beam whole, this whole complication that we have been talking about. Only based on one assumption that concrete does not exist where it has low compression. If there is a tension, concrete takes zero tension. If we make that assumption, our life will become very easy, and we will see that later. This is a finite element analysis of a beam. We divide the beam into many elements, finite element analysis, and we apply a load here. It's a beam divided into finite elements. And then we move the load to the different location, and you can see here, in fact, I wish you could see the color forming in such a way that if we combine those colors, you will see them forming a hidden truss inside. An arch is being formed. This is the compression flowing like this, tension will be here. Compression flowing like this, tension will be here. So compression, tension, and internal arch or internal truss forming inside the beam. So that means beam does not only have a pure bending mechanism, it also has an arching and a truss mechanism hidden in it. So beam is a combination of an arch and a truss and a beam, right? Depends only on the dimensions. If it is very big, it will become an arch, pure arch. If it is medium, it will be a truss. If it will be very flat, it will be a beam. So that means the dimension of the beam will determine which behavior will be predominant. And there will be some dimensions in which all three behavior will be interacting. So now we have got to another level. The beam is no longer a beam. Beam is actually a truss, or beam is an arch, right? So now it's not only the section that we are trying to understand, we are also trying to see how the size of the member affects all of this, which we will discuss in member behavior in the next, right? So we are trying to understand the entire mechanics of the things. So, however, lucky for us, the codes come to our rescue again and make the things simple for us. Sometimes simple, sometimes complicated. Design for shear is simplified to some extent. First of all, failure mechanism. Then we have to look at the dimensions, which will depend on dimension, geometry, loading, and member properties. Then shear strength models, stresses in uncracked beams, plastic truss models, ACI code design procedures, cracked beam models. That means we have to choose where we have to go, right? So, design for shear can be very complicated or can be very simple, depending upon which of these we choose. So, if the dimensions are such that Bernoulli's theorem apply, and you are using ACI code design procedure, quite simple. BS also quite simple. However, if the geometry and member properties are such that it is not a beam, it's an arch and a truss and something like that, those theorem, and it's a D region, these will not help. Then we'll have to go for another approach, right? And if you start to incorporate all of the stresses of uncracked beams and try to explain everything that we just talk about, and include all of those interactions, it becomes very complicated, right? So very simple to very complicated depending upon what type of member we are dealing with, what type of stresses, what level of stress we are dealing with. For simple cases, very simple cases, the procedure is also simple. Compute cross-section properties, that means B, D and things like that. Compute shear capacity of concrete alone based on one of the equations that we talked about. One of the 6 equations in ACI and maybe 2 equations in BS. Determine shear to be resisted by steel. So total shear, subtract concrete first, remaining is steel. Calculate the reinforcement to resist the shear. Calculate the minimum reinforcement for shear. Check whichever governs. Compute shear reinforcement separately. Select rebars and determine bar spacing for shear. Check crack spacing and limit of bars. Right? This is only when you're designing for shear. Tension being 0. Right? If you also have tension, we will talk next. Okay? Okay, so I don't want to cover too much today because we talked about a lot of things. These are some of the equations that you will actually help me find and understand. Equation number 1, equations number 2, 3, 4, something like that. I don't want to go into the details. I need you to understand how these things are working. But you can see from here that the equations can be very complicated or very simple, depending upon how many factors we include in that one. Right? And these are the things that affect those equations. Shear due to concrete, shear due to steel, steel factor load, axial load, cross section, FC prime, Fi, and then actually there are more, including, so you can see here, axial force is here, axial force is here. You will find other equation. You have bending moment also, and you have this sine alpha, cos alpha, which actually is what that angle I was talking about. But if you use alpha equal to 45, then sine all this disappears, right? This becomes 1. So that's why the equations can be simplified based on that. And normally we use AB Fi d over S because we assume 45-degree angle. But it's not true. This is only true for pure shear. It's not true for other locations. But we assume it to be true everywhere to make it easy for us.